Howdy. This video is going to be a little bit unusual because it's going to be directed to my regular physics students and at the same time to my AP physics students. What we're going to do is to create a shortcut formula called the range formula that will allow us to quickly solve certain types of projectile problems. Specifically, we're going to look at problems in which a projectile is launched on level ground. On level ground means that delta y is equal to 0. So the object goes up and it comes back to the same level that it started at. And what we'd like to do is we'd like to compute the range given an initial velocity in polar form, v0 at an angle theta 0. So that's what we're going to do in this video. After we finish that, I'm going to invite my regular physics students to continue listening if they want to, or to simply cut the video if they are done. And we will take a look at a formula that gives us y as a function of x for projectiles. Projectiles spelled with a J. And this is interesting but optional material for my regular physics students. For my AP physics students, you need to know how to do this. So, here we go. Let's first consider the question of finding the range of a projectile. And our setup is going to be that we have an initial velocity, v0 is equal to some speed at an angle at some initial angle, like that. And we're going to fire our projectile on level ground so that delta y is equal to 0. And what we'd like to do is to find the distance, delta x, which is called the range, that the projectile travels. Well, let's see. We know what to do here. We can set up a reference frame. And so we're going to put 0 at the origin right here where the particle starts. And we're going to take this direction to be positive and the up direction to be positive. And we're going to list our initial conditions. We have an initial position of 0, 0. We have an initial velocity that is going to be v0 at angle theta 0. And we know enough to know that we ought to convert that into rectangular form. So we get v0 cosine theta and v0 sine theta as our initial form. And then, of course, we have the acceleration vector is equal to 0 and negative g. I'm actually going to leave g as the symbol g rather than replacing it with 9.80 or 10 because I want our results to be valid for any planetary body such as the moon or Jupiter that we might happen to find ourselves on. And then we can just replace whatever value of g applies to the planet that we're on and get the same kind of result. So that's our setup. Now we want to translate our problem into math. And our problem is find the range r, which is delta x, when delta y is equal to 0. And so it's a fairly straightforward computation. We're going to set up x and y here. And we're going to begin with our delta y because we know that delta y is equal to 0. And that's equal to v0 yt plus 1/2 at squared. And the value for v0y is our initial velocity in the y direction, v0 sine theta 0. And the value for the acceleration is our acceleration in the y direction, which is negative g. And so this guy is equal to 0. Now we ask, well, how does that help us? Well, it helps us because we can actually solve this equation for t by factoring. As I tell my math students, all the time. Factoring is your friend, and so it is here. I have a common factor of t, can be factored out. And that gives me two possible solutions for t. One of those solutions is t is equal to 0. That's this guy right here. And the other solution is that this whole thing is equal to 0. And it looks a little bit ugly, but it's not, in principle, any different from numbers such as 2 or 3. If I solve here by subtracting v0 sine theta 0 from both sides, multiplying both sides by negative 2, there's my 2, and dividing both sides by g, I get my second solution. T is equal to 2 v0 sine theta 0 over g. Now what do these 1, 2 solutions mean? Let's go back to our diagram and see. These are the two solutions for which my delta y is equal to 0. And that happens two places on the diagram. One happens when I haven't even started yet, and that is the t equals 0 solution. And the other solution over here is my t is equal to 2 v0 sine theta over g. That's this guy right here. And I want you to observe what conditions would make this value of t large or small. If v0 is large, or if sine theta is large, then t will be relatively large. How does that happen? Well, we make v0 be large by shooting the projectile at a very fast speed, initial speed. And we make sine theta be large by making the initial angle be very large. So if I shoot the projectile really fast, or if I shoot it at a high angle, then it is going to have a long hang time. We call this time the hang time, just like you do for a football. On the other hand, if my value of g is very large, of course on Earth it's 10 or 9.80, on Jupiter it's much larger than that, and on the Moon it's only about 1.6. So if my value of g is very large, that's going to make this t very small. In other words, if my planet pulls really hard, then my projectile is going to stay in the air for a much shorter time. So the implication is that if I kick a football on the Moon, it's going to be above the ground for a very long time. If I were to kick it on Jupiter, then the whole thing would be over really quickly. Boom, we're done. Okay, so I've got my two solutions t. And now we remember that the thing that carries across the columns is t. And so if I'm looking for delta x at the time t when it hits the ground, then I can come over here and substitute for my delta x using the x component of the velocity now and the x acceleration, which is going to give me v0 cosine theta times the t that we found down here, 2v0 sine theta over g. And my second term, the 1/2 at squared, simply zeroes out because my acceleration in the x direction is 0. Gravity pulls straight down, not across. So now it's just a matter, I've got my solution for the range. I now just need to clean it up. I notice that I have a factor of v0 and a factor of v0, which is v0 squared. And then I have a factor of 2, which I'm going to write here, and cosine theta and sine theta. And all of that is divided by g. So while this is a little bit abstract, it uses the exact same method that we've been using all along to solve our projectile problems. Now comes a slight bit of trig magic. If you have already been through trig, then you may recognize this quantity right here. If you've not yet been through trig, then I'll just go ahead and tell you that this quantity, 2 times sine theta times cosine theta, just so happens to be exactly equal to the sine of 2 theta. If you haven't yet been in trig, then just accept that as a weird but interesting fact. If you have been in trig, then you recognize that as the famous double angle identity. And then, of course, all of that is still divided by g. So this is the concise expression for our range. And if you go back to certain problems, then you should find that this helps make short work of them. For instance, the fire hose problem that we solved, that I posted the solution for, number 19 in the Gene Coley book. Now, I have to issue a word of caution here. In order to get this expression, we had to make an assumption about our problem, and the assumption about our problem that we made was delta y is equal to 0. So that if I am not shooting on level ground, for example, if I'm shooting up to a mountaintop or something like that, or if I'm shooting off the top of a building, then my range equation does not apply to any of these scenarios. And that's confusing in one of the homework problems because they ask you for the range of an object that is shot just like this. They give you an object off the top of a building, and they ask you for the range here. Well, you can still answer the question by doing our usual process. The reference frame and the initial conditions and translating the problem. But now, instead of looking for delta x when delta y is equal to 0, now you have to look for delta x when delta y is all the way down here. So that's my word of caution. That's all that I have for my regular physics students. The upshot is that we have a nice concise expression for the range, which is v0 squared times sine 2 theta all over g. At this time, I'm going to turn to my AP Physics students and add or extend a little bit. So if you want to keep listening, regular physics students, you're welcome to do so. And if not, then I'll see you tomorrow. What we would like to do is to get an expression for the shape of this curve, or the trajectory of this curve. We want to find y as a function of x along the curve. And to do that, we're going to again set a reference frame of 0 right here. And it doesn't matter if we are shooting on level ground or not. We're really just trying to find all of the different y values for different x values anywhere along the curve. And of course, we're going to take plus to be in the usual manner. Our initial setup is that the initial position is 0, 0. The initial velocity is again going to be v0 cosine theta, comma, v0 sine theta. And our acceleration is again going to be 0, negative g. So the only difference between this and the previous problem is what we're trying to find, as well as the fact that we're relaxing the condition about shooting on level ground, because we really don't care about that. Okay, so now what can we say? Well, actually, it's fairly straightforward. If I look in the x direction, and if I look in the y direction, then delta x is going to be v0 x t plus 1/2 at squared. And because my initial position is at the origin, delta x is x minus 0. And because the acceleration is 0 in the x direction, then this guy goes to 0. So this gives us a nice concise expression. X equals v0 cosine theta t. Meanwhile, over here in the y direction, delta y is equal to v0 yt plus 1/2 at squared, which is v0 sine theta t minus 1/2 g t squared. And delta y is also y minus 0, so that we effectively get y. And so what we're really trying to do is to simply eliminate t, our parameter, and we're going to do it by substituting. We're going to solve for t over here, and then we're going to substitute for t into there. And so solving is just a matter of dividing both sides by v0 cosine theta. And when I substitute, I get y is equal to v0 sine theta times the value of t that we found here, which is x over v0 cosine theta, minus 1/2g times the value of t that we found here squared. Now, this looks pretty yucky, but some things clean up nicely. V0's cancel, and sine theta divided by cosine theta is the same as tan theta. And over here, I have x squared on the top, and I also have g on the top. And on the bottom, I have 2, v0 squared, and cosine squared theta. All of those things. Now, this is not an expression that you want to try to memorize because it's too easy to get things out of place. However, it is an expression that we commonly need, and so instead, I invite you to derive it for yourself a couple of times. Pause the video at this time and see if you can derive it once. Welcome back. And I'd like to point out some things about our expression. The first thing that we observe about our expression is this. Y is a quadratic function of x. And because y is a quadratic function of x, that means that the shape of my projectile motion is guaranteed to be a parabola every single time. The second thing that I want to observe is that the curvature of that parabola is determined by this coefficient right here. And in particular, we want to see what would make my parabola more or less curvy. And to make it less curvy, I would make this coefficient get as close as possible to 0. So, for example, if I were on a planet that had no gravity, in other words, I take the limit as g goes to 0, then all of a sudden this entire quadratic term disappears, and lo and behold, I get y equals tan theta x, which would give me a straight line motion. In other words, if I launched a projectile in a situation that had no gravity, that projectile would simply go in a straight line with a slope of tan theta forever. Likewise, if I have a large velocity, now we know that velocity can't really be infinite, but just in our model here, or, well, if I have a large velocity, then that's going to make for a straight line slope as well. And in particular, I want you to observe how that would happen. What this means is that as I go from a small v0 to a larger v0 to an even larger v0 to an infinite v0, then my curve gets larger and larger, broader and broader, more like a straight line. Let's see. On the other hand, if I have a planet that has a really large value of g, then that's going to force my if I have a planet that has a very large value of g, then that's going to force my projectile into a tight circle or a tight parabola like this. Whereas if I have a small value of g, then it's in effect the